All right, thanks for sticking around to listen to Secrets in the Sand. So I'm going to talk to you a little bit about how we use minerals to explore for nickel deposits. So nickel is a very important element for our renewable and rechargeable future. Everybody wants a new electric vehicle, but the batteries within these electric vehicles take a lot of resources. Specifically, nickel is 29 kilograms worth of metal in each of these electric vehicles. So to meet the demand for these renewable and rechargeable technologies, we need to find more nickel deposits. Australia is pretty well off when it comes to nickel. We produce 8% of the world's nickel metal, and it's found mostly here in Western Australia. So you can see in this Australian map, all of those green circles are nickel deposits. Most of them are here in Western Australia. Nickel deposits are found in two different types. There's nickel laterites, which are formed at the surface through weathering of rock, and then there's nickel sulfides, which is what we're searching for. These are shiny minerals that are found under the ground, and they're much higher quality, so so they go through less processing to be able to be used in those electric vehicles. The issue is that we think that we've found most of the nickel deposits that occur at the surface. So we have to start finding new ways to explore these nickel deposits underneath the sand and sedimentary cover where they're all buried. So this is where I think indicator minerals can help. So indicator minerals have been used for many, many years for diamond exploration. As many of you probably know, diamonds are formed in very, very high pressures, but they're a rare mineral. There are a lot of other minerals that are formed at these very, very high pressures that are a lot more common. So the high pressures that these minerals form at changes the mineral chemistry, which in the case of diamond indicators also changes their colour. So you can pick up a garnet, and if it's this bright red colour, you know you're in a high pressure environment. Or if you find bright green pyroxenes or yellow olivines, you know you're in a high pressure environment, and maybe you can find some diamonds. So what geologists do is find these minerals and start to follow the little breadcrumb trail of all of these minerals, follow them to where they become more abundant or bigger in size, and then we know that we're heading in the right direction toward our diamond deposit. For magmatic sulfides, where the nickel deposits are formed, it's a little bit more complicated. So nickel deposits can form at any pressure. So what we're looking for is the chemical change that occurs when we have sulfide in our system. So to make a magmatic sulfide deposit, you need molten magma flowing through the Earth's crust. This collects and melts some sediment that contains sulfur, which creates little sulfide molten droplets that exist in our molten magma. These float around and greedily steal all of the metals that are in the molten magma, which creates our metal-rich sulfide deposit. These little sulfide blebs become heavy and fall out of the molten magma and collect in an ore body for us to find. There are other minerals that are occurring in this molten magma chamber as well, and those will be our indicator minerals. And hopefully we can find a chemical signature that lets us know that there was sulfide around. There are a lot of options for our indicator minerals. The biggest hint is sulfide, which contains nickel in it. So if you find sulfide, you're probably near a sulfide deposit. So that one's an easy one. The other minerals we're looking for are olivine, spinel, and plagioclase, which are quite common in these rock types. And then we have some minerals that are less common, like spinel, apatite, milvanite, and arsenides. But they are still more common than the sulfides, so it might be able to give us clues as to whether or not we're near a sulfide deposit. The only thing is, we're not lucky enough, as the diamond indicators were, for those chemical changes to change the physical colour of the mineral. So we have to use fancy technologies to be able to understand when those chemistries change, so we know when you're a nickel deposit. So to preempt the question of what is the strangest thing I put in a device, this is a scanning electron microscope, and we use it to measure rocks, because that's what we do as our job. But because I was bored one day, I stuck an ant in there. So what you're looking at there is the eye of an ant. But what we use it for, practically in our job when we're not sticking ants in a scanning electron microscope, is to look for very, very rare mineral grains. So this is, on the screen there's a little pink grain. It's a pentlandite mineral, which is a nickel sulfide mineral. There was only one of these minerals in that entire sample, which is 2.5 centimeters big, hundreds and probably 1,000 or more grains in there. There was only one of those nickel sulfide. So that little grain is the size of a small grain of sand, and we were able to use this technology to find that it was there and understand that we're probably close by to a nickel deposit. But we can go even smaller. So on the screen we have some circles. The outer circle is the diameter of a human hair, which is 70 microns. The next one down is the threshold you can see with the naked eye, depending on your visual acuity. The next one is the diameter of a white blood cell, which is 25 microns. The black one is a red blood cell, and then the little white one is a microbe. So a little bacteria, which is 2 microns in diameter. What we were finding in some of our mineral grains are teeny tiny little sulfides, the size of a microbe, that contain sulfide and palladium and bismuth and all of these metals that we're looking for, which lets us know that this mineral was in contact with a sulfide at some point in its life. So we can find these tiny, tiny little traces of those sulfides to understand whether or not we're near a nickel deposit. But those are very, very hard to see. So let's move back out to a little bit bigger scale. So we can use the scanning electron microscope to analyze the chemistry in every single grain in one of these grain mounts. What I've done here is colour each of those grains to represent a mineral and the chemistry of those minerals. So basically what I've done is use the scanning electron microscope to be able to do what the diamond indicator minerals could do just by looking at the colour of the mineral. But instead here we've used scanning electron microscope to represent a colour of the chemistry of those minerals. So using this technique we can see when the minerals become more abundant or larger in size, and then we know we're getting closer to that nickel deposit. But it's not all smooth sailing. Not every mineral is completely homogeneous in its chemistry. So here what we're looking at is a bunch of minerals. We're looking at chromium represented in the colour red, manganese represented in the colour green, and titanium represented in the colour blue. This big grain with the insignia D on it is a pyroxene grain. And you can see that the chromium content, that red, changes through the crystal growth. So this is just like rings of a tree. As this crystal grew, it took in different amounts of chemistry, creating these rings. And each of those rings can tell us a little bit about what was going on as this crystal grew. The changes in chemistry let us know whether or not, let us know what temperatures it formed, what pressures it formed. They can even tell us how long ago this mineral was crystallized. But what we're using it for is to understand when that sulfide was introduced into the system. So not only did we use the scanning electron microscope, we can also use this technology, which is called the laser ablation inductively coupled mass spectrometer. And what that does is use a laser to drill out a very small hole in each of the minerals. It's about 20 microns, so we're looking at white blood cell size here. And what we're able to do is measure very, very small concentrations of elements. These are down to levels of parts per million, which is the equivalent to an eye drop of liquid in a fish tank full of liquid. So very, very small concentrations of each of the elements. We're able to measure almost every element on the periodic table. Here we're looking at 60 of them. And we look at the changes in concentration of these elements depending on whether it's next to a nickel sulfide deposit or not. So here I've coloured the next to a nickel sulfide deposit analysis in yellow and the not associated with nickel sulfide in green. You can see there are changes here, depending on whether or not it was near a nickel deposit or not. But this is just one set of data. We ended up collecting 18,800 laser ablation ICP mass analysis, and each of those analyses has 60 elements to look at. So it's a little bit too much for me as a single human to analyze every single element in every single analysis. So we turn to machine learning applications. So we categorized each of these analyses into whether or not it was associated with the nickel sulfide or not, fed it all into a machine learning model, and the machine was able to tell us whether or not we're near a nickel deposit and how confident it is in that prediction. And what it spits out for us dumb humans to use is a decision tree. So we shoot our little mineral with the laser ablation ICP-MS, and whether or not it has greater than or less than a certain amount of magnesium, we follow this little decision tree until we come down to a decision at the bottom. So you can see, if we followed this tree down to here, we would have a category of unmineralized, so not associated with nickel, and the fullness of that pie chart lets you know how confident the machine is in its prediction. So this one is 100% certain that that is not associated with nickel at all. This one, it's like 80% sure that that one's associated with mineralization. So it not only gives you a prediction, but lets you know how confident you can be in that prediction, which is really helpful when you're assessing an area for exploration. So that was analysing samples where we knew whether or not it was associated with nickel or not. So we decided to use those decision trees to analyse the prospectivity for nickel in regions where we didn't know whether or not there was nickel deposits around. So these are all analysis of ilmenite, which is one of the minerals that we were talking about before, as to whether or not they're prospective for nickel. So if it's a red circle, it's prospective. If it's a big red circle, then it's really prospective. So you can see that we have a lot of big red circles that correspond with this nickel belt in the south east of Western Australia, which corresponds to deposits like Nova Bollinger and Ravensthorpe. You're familiar with them. But that is just using one mineral and one technique, so just scanning electron microscope data. So if we were to use more minerals and both the scanning electron microscope and the laser ablation ICP-MS, we could come up with more confident maps of where there might be nickel deposits in Western Australia or Australia. But all of these samples were taken at the surface. They were all stream sediments, which means that our nickel deposit was probably also at the surface, which is why that mineral is sampling it. So to explore beneath our feet, we have to drill beneath our feet. So underneath the earth there is ancient topography. There are old mountains, old valleys that have since been covered up with sediments and sedimentary rock. If we can drill down into those old valleys, all of the indicator minerals that were eroded off those mountains into the valleys will be collected there. We can drill down into those valleys, collect those indicator minerals, and have an idea of whether or not there's a buried nickel deposit somewhere around in the ancient topography. So this is just one way that we can explore beneath our feet to find these new nickel resources, but it's very important for us to be able to meet that demand for new nickel resources and allow us to move forward into a renewable and rechargeable future. Thank you.